All right, and welcome to another mission training video. Today we're going to talk about system signal flow. The objective of today's training is to understand signal flow in a modern SATCOM system. All right, so from a 35,000 foot level, looking at a block diagram of the signal flow through your system, you've got your signal coming from the satellite into your antenna reflector, which is going to concentrate and reflect that signal back up into your waveguide to the low noise block down converter. The low noise block down converter is going to amplify and down convert that signal. It's going to go over a cable from the outside of your facility to the inside. On the inside, it's going to go to your power supply unit. Power supply unit's actually supplying the power that powers this LNB outside. From the PSU, you're going to go into the antenna matrix switch, and that antenna matrix switch will allow you to select which subsystem those signals are going to go to, or multiple subsystems. So your antenna reflector, that signal coming down from the satellite really far away is super weak, so that signal is going to go into your reflector. The reflector is going to bounce that signal back up and concentrate it into your waveguide. After your waveguide is your LNB. Your low noise block down converter, or LNB. As you can see here, we have on the far left, this is a C-band LNB. It is larger than these guys over here because C-band has a lower frequency and therefore a larger wavelength, so the waveguide going into it is larger. This one is a KU LNB, which has a higher frequency and therefore a smaller wavelength, so the waveguide going into it is actually much smaller than the C-band one over here. So what's going on inside your LNB is, like, for example, let's take a sample frequency. We've got 11.8 gigahertz coming off of the satellite as our target frequency. That frequency goes into the LNB, and there is a low noise amplifier that's going to amplify the signal and increase the power of that signal going into your system. The reason that we amplify the signal out at the antenna is because it is away from all of the other equipment that's inside your facility, which generates noise. We don't want to amplify noise. We want to amplify our target signal, so we're going to amplify it out here away from the noise. That 11.8 gigahertz amplified signal is going to go into a mixer. Your mixer for your LNB, for this one specifically, we just chose a local oscillator of 10.75 gigahertz. So your local oscillator on the LNB is also going to send in another signal. It's going to has a frequency that or a crystal that's vibrating at 10.75 gigahertz. It's going to send in a signal at that 10.75 gigahertz. When those signals all go into a mixer, you've got your 11.8 and your 10.75 that come out on the other end, but you also get the addition and the subtraction of those two signals. That keeps going on forever, but we're just only going to talk about our primaries here. So 11.8 plus 10.75 is 22.55 gigahertz. You get that coming out. That's the upconverted frequency. And then you get your 1.05 gigahertz, which is your down-converted frequency, and that's that L-band frequency that we want going into our system. So after that, we're going to go through a filter. I just made up this filter. This filter is a bandpass filter that will only allow anything within the frequency band of 950 to 1400 megahertz to pass through, which means these other three signals get filtered out, and the only thing that passes through is our 10.5 gigahertz, which is what we want going into our system. That's our down-converted amplified signal that we want coming in for us to use. This is just kind of a blown up picture of an LNB. You can see here that this one will take an input of 11.7 to 12.2 gigahertz. Our target frequency is at 11.8, so it's within that range, so it will work for our purposes. The local oscillator frequency on this one is 10.75 gigahertz. That's pretty much standard for this particular KU range, but that's not always the case. They could be different. Different local oscillators are going to give you different results coming out the other side. So cables. Most people don't think of a cable as being an important part of your system, but the cables going from outside of your facility to the antenna, or from inside of your facility to outside of your facility, are extremely important. They're what are going to cause you the most grief and the most heartache. These cables are going to possibly have ice buildup on them, which will weigh them down and could cause the outer conductor or the center cord to break or become disconnected from the connector or to short across each other. They also face wind, hail, all kinds of damage. Then there's also people who like to step on them, other people who like to drive over them with gators and other vehicles. So they go through a lot of abuse, and a lot of times these guys are gonna, if they are not properly taken care of and monitored and maintained, they're gonna cause you a lot of issues. The reason I'm showing you LMR 400 cable here is because it's kind of the standard. It's probably what you're gonna have on your system. I did show over here, these are some older standards that, and this is a frequency range outside of the range that we work at, but you can see the loss profiles for these guys. As you go higher in frequency, the loss becomes a lot higher. So LMR 400, the loss profile is not as steep. So if you do need a new cable and you find one of these other older, different standard cables, and you think that that's going to work for you, you might be in for a rude awakening. So just be careful with this and watch this and use the proper cable that you're supposed to, or try and source it if you can. So just even in the LMR series, we have different types of cables. So we got the 100 alpha, the 195, and the 200, 240. These guys are thinner, smaller cables. They may even work at these frequency ranges for very short runs inside of the facility, but to go for your 100-foot runs going outside, you're really going to want LMR 400 or above. LMR 600 has less frequency or less loss, but it's a lot thicker and a lot harder to bend. It's a lot less flexible. It's hard to work with. LMR 900 and 1200 it's also a lot more expensive, are a lot more expensive, and they're almost impossible to work with like on a daily basis. These are what you would want to put in if you were doing an install for, something that's going to stay in the ground for 20 years. LMR 400 is pretty much what we're going to stick with. I just wanted to show something here too real quick. We have 15.5 dB of loss at our L-band frequency at 100 meters. 100 meters times 3.2 is roughly 320 feet. So at 320 feet, this cable is unusable. So we need to keep our runs short, keep our antennas close and our runs as short as possible. Also, sometimes people think that if they have 100 foot of cable and they need 110 feet of cable to make their run work, that they can just stick a connector between the two and have a 200 foot length of cable and run it in the facility and they're good to go. I did a real quick calculation at L-band to show you at 100 feet, you have 4.6 dB of loss, and at 200 feet, you have 9.2 dB of loss, which dB is a ratio and it's logarithmic. So if you remember from that, 3 dB is double. So this is greater than double the amount of loss for a 200 foot run. And that's not including that connector that you put between the two cables, which probably is going to add another 3 dB to it. So this is also not going to work for our purposes. You got to keep those cable runs short. All right, so from the antenna reflector to the low noise block down converter across the cable, now we're inside the facility and we enter the LMB power supply unit. So if you look here at this LMB, you'll notice that there is no power cable going to it. There's only one input, except you got the input coming from the waveguide here, and then you've got this RF input going into it. The way that we get power to this guy is the power supply unit sends a voltage over this RF cable. It uses this outer conductor as the ground, and it uses this center pin conductor to push the 18 volts DC into the LMB. That's what powers our amplifier and our down converter inside of this guy right here. A common mistake I see people do is whenever they are trying to use a spectrum analyzer outside of the facility, they'll just unplug this cable, plug their spectrum analyzer into this guy, and think that they're going to see the signal coming off the satellite. Unfortunately, this guy's not powered at that point, so it's not going to amplify, it's not going to down convert, you're not going to see anything. So make sure that you let that power go through there in order to power that LMB. This is a real quick block diagram of what's going on. The red here shows the RF traveling this direction to the LMB power supply unit, and then the LMB power supply unit providing that 18 volts in order to power that LMB. So that was a very simplified version, and that is kind of displayed up here on top. you have one voltage that your power supply unit's providing to an LMB that takes one voltage and has one local oscillator. It is possible to have an LMB that covers multiple bands or multiple frequencies within one band. The way that works is your LMB power supply unit can provide multiple different voltages to switch you between bands or between frequencies. So here is just, on our LMB power supply unit, we have 3 different voltage options. We went with 18 volts. That selected this 10.75 gigahertz local oscillator, which put us into that KU mid-range band that we were just talking about before. If we wanted to do a KU high frequency band, we could send, if we had the proper LMB that has multiple local oscillators on it to give us multiple frequency down conversions, right? We could send 12 volts across the line. 12 volts would select the 9.2 gigahertz local oscillator as opposed to the 10.75, which would give us a higher frequency, that higher frequency range, which is where we're trying to get to with that LMB or with that KU high. This is just a picture of a LMB power supply unit. There's nothing really too fancy about it. You've got your power going into it. You've got RF in and DC out here. As you can see, all of these are going to the antennas to power LMBs and take the RF in. And then you have your RF out going out, which is going to go down to your matrix switch. So now we just crossed the line from the LMB power supply unit to the matrix switch. The matrix switch is going to allow you to select which subsystem your RF signals are going to go to, or it can go to multiple ones. So this is just kind of look at the back panel of an RF matrix switch. The RF matrix switch has a lot of inputs and a lot of outputs, and all you're really doing is you can select from what input you want it to come into to what output you want it to go to, if any at all, or none. This is a very simple, simplified version of it. As you can see, I did 3 3.7 meter antennas and 2 4.2 meter antennas, and I only did one input coming from each antenna. You're actually going to have 2 coming from each antenna, but it would start to make this diagram look really busy if I would have added horizontal and vertical poles coming from each antenna. So we're just going to go with this simplified version, and you can see here you can take your input coming from your 3.7 meter antenna 1 and you can select it to go to your spectrum analyzer. You could select it to go to your DVB subsystem. You could select it to go to any of your other subsystems, wherever you want it to go, or you can go to multiple ones. Same with all of the other ones. So here I just kind of did a little bit of patching. This is going to be a software interface, by the way. But I did a little bit of patching to push our 3.7 meter antenna 1 is going to go only to our DVB subsystem. Antenna 3.7 is going to go to the DVB subsystem also. And our 3.7 meter antenna 2 is going to go to our signal characterization or our spectrum analyzer. 4.2 meter antenna 1 is going to go to subsystem 3, and 4.2 meter antenna 2 is going to go to subsystem 4. And that pretty much concludes the signal flow of this actual of this system. But what I wanted to do is I wanted to talk about a little bit about what happens once your signal goes to these different subsystems. Almost all of these subsystems are using some type of software-defined radio in order to process that signal. The radio on the left here is a Harris PRC 117 Golf. It is a hardware radio. It costs about $60,000. It is super heavy, super clunky, super bulky. It's a backpack radio, but it's heavy, and then carrying batteries to go with it are even heavier. But this guy uses hardware-based radio, so it's much more rugged. But with our fixed installation site, indoors, and temperature-controlled unit, all of that stuff, the better solution for us would be to use some type of non-hardware-based radio. This guy's actually capable of line of sight and UHF SATCOM. But instead of using that, we could use a software-defined radio. On the right here is a Hack RF1 software-defined radio. These can go anywhere from $80 for just the card if you source it in China to about $350 on Amazon if you get it with a kit that has the shielding and the case and antennas and all the other little things that go along with it. This is a Red Rapids card that plugs into one of your, it can go into a server. Generally, they're used to go into servers. It's an SDR card. Last time I sourced one, it was a receive only. About $300 is what they cost. And this is a RTL SDR, which is just a little USB receive only software defined radio that goes for about $22 on Amazon. Some of the pros and cons of SDRs is that the pros is that it's cheaper. And when I say cheaper, I mean orders of magnitude cheaper. It's software upgradable. So with hardware radios, when they come out with a new modulation scheme or technology advances, you have to buy a whole new radio. And with what we do, or with what the military does, sometimes buying a whole new radio means you got to buy whole new radios for everybody, which is a lot of radios, lots of $60,000 radios instead of a much cheaper solution. Some of the cons is that it requires a computer to process it. So as you can see with the Red Rapids card, it goes into a server. With the little USB ones, you need a laptop in order to plug those into. But the biggest thing that we have an issue with is that they're not very rugged and that they're sensitive to your signal input. We do a lot of signal conditioning, making the signal the right power levels, filtering out unwanted and unnecessary stuff from those signals before we put them into the SDR. If you look here, this is actually this little portion, the analog to digital converter and the digital to analog converter. This is the only part that's the actual SDR. Everything on this side over is it's just software based, and everything on this side over is really just it's our other hardware stuff, like our LMB is what would take care of this. But we're going to condition that signal before it goes into this analog to digital converter. In the event that you have any type of power fluctuation or your signal conditioning unit doesn't do exactly what it's supposed to do, if it gives this SDR a signal that it doesn't like, it will lock up on you. And the best way in order to clear that out, you can keep trying to play with the software. You can shut down your software that you're using, bring it back up and keep trying it. Most of the time, you're still going to have that problem. The way to clear probably 98% of the faults when it comes to these cards is to shut down the server that they're in, remove power and remove RF from them for a few seconds, plug all of it back up, power it back up, and it will fire back up. And 98% of the time it's going to work for you after that. So that's what they're susceptible to. Whenever you get those errors, that's usually the fix for it. So that was really the point I wanted to drive home by kind of diving down deep into the SDR world. I did want to show you real quick another thing too. Those little $22 receive only USB things that you can get on Amazon. Most people don't know this, but aircraft talk to each other via HF when they're traveling over the ocean. There aren't VHF antennas every 50 miles like there are here on mainland. So they have to talk and using that really low frequency that travels across continents. And you can use that 22. This is just an example of someone using that $22 SDR in order to listen to those HF signals coming from aircraft crossing the ocean.
Secondary frequency for Shamrock Radio, 8879er. That's 30 West contact Gander on primary frequency, 8864. Secondary 11279er. And cell phone check is coming.
All right, and that's all I have for you today. I'll let the crows play us out.